Okay, so far we covered integrity and authenticity in the symmetric key world, namely MACs, where the two parties share the same key. But now let's look at the asymmetric world. What happens when Alice and Bob don't share the same key? How do they have integrity and authenticity? And for that, we use digital signatures. So digital signatures. And these are also heavily used whenever you communicate on the web with the website and establish a secure connection. We'll see when we learn about TLS that you basically use a digital signature every time. So you have, again, Alice and Bob. And Alice has her secret key and public key. Just like with public key encryption, the same thing shows up for digital signatures. And Bob has his secret key and his public key. And here we're concerned with integrity and authenticity in the asymmetric setting. So we're not concerned with confidentiality. So if Alice wants to send this message M, she can also sign it with her secret key to produce a signature SIG. And Bob can verify using Alice's public key. So all you need to verify that the message comes from someone is their public key, this message and the signature, and he's going to get yes or no. Okay? So the signature proves that Alice produced this message. Okay? Only the holder of the secret key of Alice could have produced the signature, because as with Macs, signatures are going to be unforgeable. Okay, so let's treat them the same way as we did with any other crypto primitive. Let's look at the syntax, let's look at correctness and security. So for the syntax, we have the following. We have the key generation algorithm that produces a secret key used for signing and the public key used for verifying. Then there's the signing algorithm that uses a secret key and the message M and produces a signature. And then there's the verify algorithm that uses the public key, the message and the signature, and outputs 0 or 1 if the signature verifies. So in terms of correctness, what you want is that if you sign a message with the secret key, then you're going to be able to verify it using the public key. Okay, so for correctness, for all messages M, secret key and public key, if you verify with the public key on the message, the output of sign with the secret key on that message, you're going to get yes, a 1. Yes, this is verifying. That's correctness, so that's important for the signature scheme to be usable and functional. But then for security, we're going to have a very, very similar definition to the Mac, namely existential unforgeability. So security is existential unforgeability under chosen plaintext attack. So again, existential unforgeable under chosen plaintext attack. And the definition is, again, very, very similar to the Mac, but in this case, the challenger uses a signature box as opposed to the Mac box. So I'm just going to remind you really fast. So you have the challenger and adversary, and this challenger is going to generate secret key and public key and going to post the public key, make it available. The adversary sends messages, hey, can you please sign MI for me? And the challenger is going to respond with sign of SK and MI, and this can repeat many times. And then the adversary is supposed to come up with a message M and M prime that is different, so different from any of the messages as before, and the correct signature on the message. So and the probability that, and if this signature verifies, then the adversary wins. So add wins if M prime is different from any of the MIs, and verify with the public key on M prime of sig says yes. Okay, then the adversary wins. So what we want is the probability that, for all adversaries, the probability that the adversary wins in this game is negligible, equals or is negligible, whichever way. Okay, so this is the same game as for max, and basically what it says that, look, the adversary can get as many signatures as he wants for different messages, but he won't be able to forge a signature for a new message. He should not be able to forge a signature for a new message.